Gyroscopes.
Spinning devices whose actions revolve around a mounted wheel that spins rapidly about an axis which is free to move in any direction. Incredibly, the axis's orientation is not affected by the tilting of the mount of the axis, so gyroscopes can seemingly defy gravity. But why? What makes gyroscopes apparently weightless? Before getting mixed up with any more lengthy definitions, let me demonstrate. Take this wheel for instance. It falls, but if I spin the wheel before I drop it, it spins and does not fall. This phenomenon can be described through pages of mathematical analysis or through a few concise demonstrations. You see, when the wheel is stationary, gravity acts on it, causing the top of the wheel to move left and down, causing the bottom of the wheel to move right and up. This is expected. When I spin the wheel, points at the top of the wheel do still fall left and down, but since the wheel is in motion, those same points a split second later are now at the bottom of the wheel, and the left and down motion is now flipped. So the points at the bottom of the wheel now want to move left and up. This is inversely true for the bottom of the wheel. At the bottom, the points at the bottom want to move right and up. But when I spin it, they're now on the top, and that motion flips. So now at the top, they want to move right and down. Due to the constant switching motion about the axis of rotation, the wheel remains upright, spinning in a circle, because it cannot decide which way it wants to fall. Don't forget, this switching motion happens for every bit of the wheel's mass throughout its rotations, not just at the top and the bottom. We see this with the tilting and rotations of the gyroscope. When the gyroscope tilts right due to gravity, the mass tilting right immediately finds itself tilting left because the rotations are so quick and offset the tilt of the gyroscope. When the gyroscope spins very quickly, we do not notice the switching of the tilt at all. The gyroscope will remain upright until friction slows the gyroscope to the point of precession. The tilt takes effect, and the gyroscope will subsequently fall. To go further into the topsy-turvy topic of the gyroscope, let's address gyroscopic precession. Gyroscopic precession means that if you apply a force at any point on a rotating object, the force will take effect 90 degrees later in the rotation. This can get a little complicated, so let's take a look at it, this time with a gyroscope rather than a bike wheel. This gyroscope has a torque acting counterclockwise, causing the gyroscope's flywheel to spin. We know, due to the right-hand rule, that angular momentum in this case is pointing out of the top of the gyroscope. Gravity is a downward force and creates a torque about the base point of the gyroscope. This torque reacts with our previous system and creates a net torque, which then reacts with our angular momentum. Angular momentum changes based on the direction that the net torque points. So in this case, our gyroscopic precession is due to the torque created by gravity, which therefore affects the orientation of our angular momentum. Now that we've scratched the surface, let's explore gyroscopic precession in the real world. A common medical tool, the magnetic resonance image, or MRI, uses hydrogen atoms in water to create an image of the body. Hydrogen atoms as nuclei have an angular momentum because they have an uneven amount of protons and electrons in the atom, creating a net spin. The magnetic resonance image uses a magnetic field to create a nuclear compass, which then creates atomic precession. Atomic precession releases small electronic pulses, which are then used to map out tissues in the body. The neatest example of gyroscopic precession I can think of is of the helicopter. Many people wonder just how helicopter steering works. You may have thought, previous to this video, that in order to move the helicopter forward, you would need to create a lift force on the back blade, which would tilt the blades forward and move the helicopter forward. But with your newly acquired knowledge, you now know this wouldn't work. Because the blades are in rotation, any force that is applied will take effect 90 degrees later in the direction of the rotation. Sort of like gyroscopic precession or something. So, in order to move the helicopter forward, whose blades are moving counterclockwise, you would need to create a lift force on the left side so that it would take effect 90 degrees later on the back. The blades would then tilt forward and the helicopter would move forward. Makes sense, right? Tops, frisbees, boomerangs, aerial navigation systems. Heck, even Mother Earth is one giant gyroscope. Gyroscopes are incredible and can be found everywhere. Now go outside and find one for yourselves. Thanks for joining me, and I'll see you around.